All right, day 12, starting now. I see. Okay, it's just a graph, and all k's at most once. All cave. Okay. That's nothing. And I guess is that it? The add and anything else. Spell. Why am I putting two things? Something. Right answer. Okay. 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 Pretty good. So what's going on? So we have a graph problem. And we're basically doing BFS on this graph. Yeah, that's fine. Okay. So what's going on? We had this input, and there's like 4 different types of vertices in the graph, right? So the graph is just a bunch of nodes connected by edges, right? This is the sort of CS, like abstract math definition of the graph. So we have a special node start, a special node end, and then nodes in the middle. And the nodes in the middle are either lowercase or uppercase. So you can see that start is connected to like a couple different nodes, and end is connected to a couple different nodes. And then we have some uppercase things like xy and some lowercase things like bm. And so the rule is that we want to find paths to the graph from start to end. And we aren't allowed to go through any of the small nodes more than once, but we can go visit big nodes multiple times. So like start, A, end is one path, but so is like start A, C, A, end. But we can't go start A, C, A, C, right? That's visiting C twice. And in fact, I think we can never visit D because we'd have to go back to B. See, none of these paths visit D. D, rather. Right. So first we go through the list of edges, and then we just keep track for every node which vertices are next to it. This is called an adjacency list. It is basically always the right place, the right way to store a graph. And now we're going to do our, it's not really a BFS, right? We want to know all possible paths. So we're basically just going to trace all of those paths out. And I sort of set this up so that we could like have a minimal state. You could also just remember the entire path that you traversed, but I'm just remembering the important things about the path. So where we are, which small caves we've visited. And in part 1, this case does not apply. So let me just talk to you part 1. So where we are, which small caves we visited, and this thing for part 2 that I'll talk about in a sec. So count how many paths, and initially, like, this is the start state, right? We're at start, we can't go back to it, and that's it. So pop off a state. If we're at end, we're not allowed to like go back from end and then come back to it later. So if we're at end, that is a valid path. Increment the answer. Otherwise, for all of our neighbors, if we haven't been there before, right, this is sort of our set of nodes that we can't go back to. So if we haven't been there before, then we're going to like consider going there, right? So that brings you to this new place. And if it's a small cave, right, that is, if it's lowercase, then we want to add it to the list of prohibited nodes that we can't go back to. So that's pretty much it for part 1, is you just trace out all those paths and, return how many there were. In part 2, we had this extra constraint that we're allowed to go through one of the small paths twice. One of the lowercase things twice. It can't be started and end. So I've added this other piece to our state, which is which small cave we visited twice. And now there's this extra case, which is if we already visited this cave once, but we haven't visited any cave twice, and it's not the start of the end, we're not allowed to visit them again, and we're in part 2, then we can go to there, and we'll just mark down that we've actually used, this ability to go to a cave twice. I guess technically we don't need to store the actual cave that we went to. This could just be true or false, but whatever. And you can see that this does fat print 3887 and 104834, so that looks correct. And yeah, so this is pretty much just brute force through the graph, tracing all possible paths. Luckily, the graph is small; it's only 13 vertices, so this, there's not too many paths. In a larger graph, like you wouldn't be able to trace all these paths; it would just take forever. But the problem does ask us to count all the paths, and there's not really a good way, like a more efficient way to do that. Like brute force is the best way. And as I mentioned, instead of like keeping track of this compressed state of like just what we care about, you could probably actually just do fine keeping track of the entire path here. Maybe it would be slow for part 2, I'm not sure. Keep track of the entire path here, and then just like check, is this thing like already in my path? I sort of compressed it by instinct, which is what you would do if you wanted like the shortest path or something. You might need to do something like this, or like the longest path, I don't know. Some kind of dynamic programming thing. I think that's about all there is to say about day 12. See you tomorrow.